So, what is our aim in microscopic model of current? We found the current, then we found the current density, and we related the current density with the sigma, what is called conductivity. This is called microscopic form of Ohm's law. Next is macroscopic form of Ohm's law. This is what we all know, very famous relationship. Macroscopic form of Ohm's law. So, what we derived previously, J is equal to sigma into E. And what is J? J we all know, I by A is equal to sigma into E. So, imagine a conductor. So, in the previous case in microscopic model, we have chosen a small volume element of length say dx, and in that we have found the movement of electrons or current in that one, and or current density. Now here macroscopic, macroscopic means for the entire conductor we are going to find entire conductor. So, let us take a conductor of length say L. You are applying a potential difference say V. The electric field that is produced due to the potential be say E, and I be the conventional current direction, and we all know E is equal to V by D, where V is the potential difference and D is the length of the plate. So, here length is say L, so E will be V by L. I by A is equal to sigma into V by L. So, V by L, I rearrange this, sigma V by L is equal to I by A, or V is equal to I L by A into sigma. So, length of the conductor, area of cross section, let us imagine area of cross section of the conductor be say A, and sigma, as I said, it is the intrinsic property of the conductor. So, all these are constant. So, I give the name as a R, I into R. So, this is the macroscopic form of Ohm's law. V is equal to IR, or we can write V by I is equal to R. What is R? R is nothing but the resistance offered by the conductor. Resistance offered by the conductor. So, what is R actually? Here we have taken R is equal to L by A into sigma, and I said rho is equal to 1 by sigma. So, this can, other words, R can be written as rho L by A. So, if you take resistance R depends on length and R depends on area of cross section. I have not included rho or sigma because I said earlier rho and sigma, they are intrinsic property, depends upon the number of carriers, the collision time, etc. So, that I will be explaining in the resistivity part, I already told. So, as length of the conductor increases, the resistance also increases. Similarly, if the area of cross section, so if the area of cross section is bigger, So the resistance offered by the conductor will be lesser. So this is directly proportional and this is inversely proportional. Now if you take this one, this relation V is equal to IR. We can write V is directly proportional to I. But this is not true all the cases, because what Ohm's law states means at a constant temperature this relationship holds good. That means when the current flowing through the conductor is steady, then the temperature is constant, then we can say V is directly proportional to I. But this is not the case for all the conductors. Say for example, if you take wires, resistors, heating elements, all these obey this law. That is, if you vary the voltage and if you measure the current, you vary the voltage and if you measure the current, so you will be getting a straight line like this. You will be getting a straight line like this. This holds good only if you connect a wire or resistor or any heating element. In this case, if you take a slope, this gives you difference in I and this gives you difference in V, and we all know slope is dy by dx, so del I by del V, and this will give you 1 by R. Or if you want to find the value of R, we can find 1 by slope. 1 by slope. And this is actually a constant. Wherever you take the slope, we get the constant value. So the resistance is constant over here in this case. So the materials that obey this Ohm's law, they are called as linear devices or linear ohmic devices. I said earlier that only these materials they obey Ohm's law. But this is not the case for materials such as diode, transistor, vacuum tubes, thermistor and all. So in this case, if you draw the VI graph, characteristic of VI graph, it will be like this. See, the graph is not linear as in this case. So here we cannot measure the resistance. So we cannot say the resistance is constant. So these devices are called as non-ohmic or non-linear devices. So we found macroscopic form of Ohm's law, that is V is equal to IR, and I said this law holds good only at a particular temperature and when the current is steady. If the resistance is constant, then VI graph is linear, then they obey the Ohm's law. Otherwise, these devices are called as linear or ohmic devices, and non-ohmic, non-linear devices, they won't obey the Ohm's law. Now let us see what is resistivity. So resistance is different from resistivity. I said R is equal to rho L by A. This is the resistance. Or we can write R is equal to L by sigma into A. But if you take resistivity, I rearrange this formula. RA by L. So what is resistivity? Resistivity is the resistance offered to the current flow by a conductor of unit length having unit area of cross section. This is an important definition. So what is resistivity? Resistivity is the resistance offered to the current flow by a conductor of unit length, that is L is equal to 1 meter, area is equal to 1 meter square, imagine. So then resistivity is equal to resistance offered by the conductor. This is the definition for this one. And what is its unit? We know resistance is ohm, area is meter square, and length is meter, so its unit is ohm meter. Actually, this resistivity is constant for a particular material at a particular temperature. This is very, very important. At a particular temperature. Actually, resistivity, it is constant. Say for example, if you take copper, it has certain resistivity. This is actually a conductor. So copper has certain resistivity. Similarly, if you take any metals, semiconductors, all materials, they have different resistivity. See here. See, these are the materials and resistivity. See the top at 20 degrees Celsius. That is very important. I said resistivity is constant for a particular material, but at a particular temperature, because if the temperature varies, automatically the resistivity value also will be changing. So this is an important thing we should remember. So why the resistivity is changing? See, actually if R is changing, A is changing, L is changing, what about resistivity? No, there is no change in resistivity, because this resistivity does not depend on R, A or L. It actually depends upon the, I said earlier, it is intrinsic property, and rho is m by n E square tau. So see this equation, mass, rho depends upon mass of electron, electronic charge, number of free electrons, and as well as tau. Tau is the average collision between two successive collision, time taken between two successive collision. So these are all intrinsic properties. These are all intrinsic. It does not depend on dimension. Rho or sigma does not depend on dimension. As I said, or resistance I told. Resistance I showed. If you change the length, actually resistance also increases, decreases. Area increases, resistance decreases. But this is not the case for resistivity or sigma, because these two are intrinsic properties. I said if the temperature changes, resistivity also changes. So if for example, if you take a conductor, any conductor, if you take any conductor, as temperature increases, resistivity also increases. As temperature changes, resistivity also changes. Why the resistivity is changing? As temperature increasing, what happens? The time taken will be less. Time taken between, because the electrons, they will be moving very fast in a conductor. So the time taken between the collision will be less. If it is less, the resistivity will be more. So resistivity will be increasing in the case of conductor. But if you take semiconductor or insulator, actually this is called as temperature increases, resistivity decreases actually here. Why the resistivity is decreasing means, here in the case of semiconductors or insulators, we have limited number of charge carriers. We are not having more carriers as in the case of conductors. So what happens, as temperature increases, of course the time increases, but the number of free carriers also keeps on changing. So it increases. If it increases, resistivity will be decreasing. That is the case. So as temperature increases, resistivity decreases. This increases, so increases, temperature increases, resistivity increases. This is called positive temperature of coefficient of resistance. So all conductors, they have positive temperature of coefficient of resistance, and all semiconductors and insulators, they have negative temperature of coefficient of resistance, because as temperature increases, resistivity decreases. This is the case. So as I said, resistivity, it's an inherent or intrinsic property, resistivity or conductivity, whereas resistance is different. So conductor, in the case of conductor, as temperature increases, resistivity also increases, because in conductors we have large amount of charge carriers. So as large amount of charge carriers we have, what happens? As they move very random manner, they collide, the time taken will be less, so it will be more, resistivity will be more, or resistance offered by the conductor will be more. But in this case, actually the conductor, the free electrons or charge carriers are less in this case. So what happens? Even though the time is decreasing, what happens? This will increase, so automatically rho will be decreasing. This is the case. So resistivity is constant for a particular material at a particular temperature. This is very, very important concept. So if come to this one, I said rho is resistivity, its unit is ohm meter, and we all know sigma is 1 by rho. So 1 by rho. So what is its unit? 1 by ohm meter. So ohm inverse, meter inverse. This ohm inverse otherwise called as mho. So mho meter inverse is the unit of conductivity. This is resistivity. This is conductivity. And resistance is, unit is ohm. So reciprocal of resistance is called conductance. Conductance. It is 1 by R, and its unit is 1 by ohm. So ohm inverse, so it can be ohm. That's all regarding resistivity.